Hey guys, tonight we uncover the mystery behind the color of the sky. Look up, what do you see? A vast, endless canvas of soft blue stretching across the horizon. It's one of those simple wonders that somehow doesn't make you stop and wonder, until now. You've probably been told before that the sky is blue because of the way sunlight interacts with the atmosphere. But what if I told you there's more to it than that? What if I said this seemingly basic question has baffled people for centuries? Yes, scientists have been puzzled for a long time. And now we're about to dive into the science that reveals why the sky is blue, and maybe uncover some quirks along the way. Just don't get too comfortable. You probably won't survive this journey without a little sleepiness creeping in. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment too. Let me know where you're tuning in from and what time it is. I'm curious how far this sleepy journey spreads. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Let's start with the basics. Light. Imagine you're standing outside in the middle of a clear day, squinting into the bright sun. That blinding white light you're looking at isn't just white, it's made up of a full spectrum of colors. Picture a rainbow, but not the soft arc that appears after a storm. Instead, visualize the spectrum of sunlight stretched out in front of you like a high-speed train, packed with all the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. In scientific terms, sunlight is made up of electromagnetic radiation, which can be split into different wavelengths. Each color we see represents a different wavelength of light, with red having the longest waves and violet the shortest. When all of these waves come together, they form the light we know as white. Sounds simple enough, right? But here's the catch. This whole process gets more interesting when sunlight enters our atmosphere, as you'll soon see. Let's start with light. What makes it? Well, light. We're talking about electromagnetic radiation. That's a fancy way of saying that light is energy traveling in waves. These waves can be long or short, fast or slow, but what really sets light apart from other types of energy is that it's visible to us. And what gives light its color? That's all about the wavelength. The longer the wavelength, the redder the light appears. The shorter the wavelength, the bluer it looks. This is the basic idea behind the color spectrum. The colors you see are part of what's called the visible light spectrum, and each color within that spectrum corresponds to a specific wavelength. For example, red light has the longest wavelengths, around 700 nanometers, while violet light has the shortest, at about 400 nanometers. Between them, you've got the full rainbow of hues. Now, light doesn't just hang around like a lazy summer cloud. It travels in straight lines. But once light hits a surface, or passes through an environment, things get complicated. If you've ever held a magnifying glass under the sun and watched how it focuses light to a single point, you've seen the raw power of light. But instead of focusing, light scatters, and that scattering is where the fun begins. Let's think about the Earth's atmosphere for a second. It's made up of gases, mostly nitrogen and oxygen, along with some dust and water vapor. As sunlight enters the atmosphere, these molecules interact with the light. They absorb some wavelengths and scatter others. The key here is that shorter wavelengths, like blue and violet, are scattered much more than longer wavelengths like red. This scattering of light in all directions is called Rayleigh scattering, named after the British scientist Lord Rayleigh, who discovered it in the 19th century. So why do we see blue instead of violet? Well, our eyes are much more sensitive to blue light than to violet light. In fact, violet light is scattered even more than blue, but because our eyes don't respond as strongly to it, we end up perceiving the sky as blue. Isn't that wild? The very thing that makes the sky blue, the scattering of light, has a couple of factors at play, from the sunlight's composition to the sensitivity of our eyes. It's a perfect storm of nature's brilliance and our biology, making the sky seem more inviting with every glance. Why does the sky look blue? Well, to answer that question, we need to get deeper into the Rayleigh scattering effect. The science behind this is pretty fascinating, so let's take a little detour through the physics of light. Remember when we talked about light as electromagnetic radiation? Here's where things get fun. When light from the sun enters Earth's atmosphere, it comes into contact with all the gases and particles floating around in the air. But it's not like the light simply passes through. No, it gets scattered in every direction, bouncing off molecules and tiny particles. Now, Rayleigh scattering works by the principle that shorter wavelengths of light, blue and violet, are scattered much more than the longer wavelengths like red, yellow, and orange. The short wavelengths get knocked around more easily because they have less energy. Think of it like trying to hit a ping pong ball with a tennis racket. The ping pong ball moves and bounces all over the place, while the tennis ball moves in a much straighter, less bouncy line. The same principle applies to light waves. Blue light, with its shorter wavelengths, is scattered more because it's like the ping pong ball in this scenario. Red light, with its long wavelengths, is less impacted by scattering and travels through the atmosphere with less deflection. This means that as sunlight hits our atmosphere, more blue light gets redirected in all directions than any other color. That's why, when you look up, your eyes are picking up all this scattered blue light, filling the sky with its color. The reason the sky doesn't look violet, even though violet light is scattered even more than blue, has to do with two things. First, our eyes are way more sensitive to blue light than to violet. Second, much of the violet light is absorbed by the upper atmosphere, especially by the ozone layer, which filters out harmful ultraviolet radiation.
So the next time you look up and admire that bright blue sky, remember that it's a mix of science and human biology working in harmony. We're looking at light that's been scattered in all directions, but it's our eyes' sensitivity to blue that makes it the standout color. All then, just to add some quirky fun to this, scientists still argue whether the sky would actually look more violet to us if our eyes were more sensitive to it. Imagine that, an entirely different sky color. But hey, that's a debate for another time. The magic of wavelengths. This is where things get really interesting. The light we see is just a tiny sliver of the entire electromagnetic spectrum, which is made up of all kinds of energy waves. These waves travel in different lengths, from extremely short waves, like gamma rays, to incredibly long waves, like radio signals. But when it comes to the visible spectrum, the colors we see in a rainbow, each color corresponds to a specific wavelength of light. It's almost as if light has its own personality, each wavelength representing a different flavor of light. The visible spectrum ranges from violet at the shortest wavelength, around 380 nanometers, to red at the longest, about 700 nanometers. Within this spectrum, each color we see, blue, green, yellow, and so on, fits neatly into its own little box, with distinct wavelengths. Blue light, for example, has a wavelength of around 450 nanometers. That's just the right size to scatter and make the sky look the way it does. When sunlight reaches Earth's atmosphere, the shorter wavelengths, like blue and violet, are scattered in all directions, which is why the sky predominantly looks blue to our eyes. But here's where it gets even more fascinating. Light waves don't just behave like the waves you see in the ocean. They interact with the molecules in the atmosphere in a very specific way based on their size. Longer wavelengths, like red, orange, and yellow, are less easily deflected by the air molecules. They move in straight lines, essentially cutting through the atmosphere. This is why the red hues from a setting sun can travel through more of the atmosphere before getting scattered, giving you those beautiful sunsets that look more red or orange than blue. It's not just about scattering, though. There's a delicate balance between the wavelength of the light and the way it interacts with the air around it. The blue light, being scattered so much, can make the entire sky appear uniformly blue. But think about what happens when sunlight enters during different times of the day. The angle at which sunlight hits the atmosphere changes, and so does the color. During the day, when the sun is overhead, we get a lot of blue light, but during sunrise and sunset, the light has to pass through more of the atmosphere, scattering even more of the blue and green wavelengths, and leaving us with reds, oranges, and purples. Wavelengths, atmosphere, and time of day. Each one plays its part in shaping the sky's color. It's nature's light show, happening all around you every single day. What happens when sunlight hits the atmosphere? Well, things start getting even more complex than just scattering. The interaction between sunlight and the atmosphere is a symphony of tiny molecules, particles, and gases, all working together to shape the sky we see. Let's take a step back and break down the process. Sunlight, as we know, is made up of a spectrum of colors, and when it enters Earth's atmosphere, it doesn't just zip through unimpeded. Instead, it collides with molecules and particles in the air. Everything from nitrogen and oxygen to water vapor and dust. You can think of these molecules like little bouncers in a club. They don't just let the light pass through easily. They stop it, bounce it, and send it off in all directions. The result? Scattering. The more molecules and particles there are in the atmosphere, the more scattering happens. But here's the kicker. Not all molecules are created equal when it comes to scattering light. Oxygen and nitrogen, the two most abundant gases in the atmosphere, are the main culprits when it comes to scattering blue light. These molecules are just the right size to efficiently scatter the shorter wavelengths of light, like blue and violet, but they don't interact as much with the longer wavelengths, like red or yellow. In fact, nitrogen and oxygen are so efficient at scattering blue light that they cause it to spread throughout the entire sky, filling our vision with that bright blue hue. However, other particles in the atmosphere, like dust, pollution, and water droplets, can alter this scattering. For example, on a particularly hazy day, the sky might appear more muted, even gray, because the dust and particles in the air scatter light in all directions, making it harder for the blue light to stand out. These particles tend to scatter all wavelengths of light more evenly, which is why the sky can look pale or even overcast at times. It's all a delicate dance between light and the molecules of the atmosphere. While blue light gets scattered most, the amount of scattering that happens depends heavily on the conditions of the atmosphere. On clear, calm days, the sky is often bright and blue, while on hazy days or after a storm, you might notice a shift in color or a dullness in the sky's usual vibrancy. It's like the atmosphere is playing its own game of hide and seek with sunlight, and you get to watch the results from your cozy spot on the ground. And here's the part that blows some minds. The scattering of light in the atmosphere isn't just a random accident. It's a highly ordered phenomenon that scientists have been studying for centuries. Yet the exact way light behaves when it hits different atmospheric layers is still a subject of debate. Scientists still argue whether other factors like the thickness of the atmosphere play a more significant role in scattering than previously thought. So while the basics are understood, there's always something new to learn. The surprising impact of air molecules. This is where things get even more mind-bending. We've talked about how sunlight interacts with the atmosphere, but it's time to really dive into why air molecules like nitrogen and oxygen are such key players in creating the blue sky. While you might think of them as the unsung heroes of the natural world, without them, the beautiful blue sky you see wouldn't even exist. It's all about their size and how they interact with light on a molecular level. When sunlight passes through the atmosphere, it's made up of many different types of light waves. The shorter wavelengths, like blue and violet, get scattered much more easily than the longer wavelengths like red and yellow. Why? Because of the size of the air molecules. Well, these molecules are small enough to interact with light waves, but not too large to cause massive disruptions. Think of them like the perfect size to be in the right place at the right time to scatter those short blue wavelengths. All when sunlight hits these molecules, it sends the blue light bouncing in all directions, filling up the sky. Now, let's throw a little twist into this. You might be wondering, why don't we see violet instead of blue, since violet light is scattered even more than blue? It's true, violet light is scattered more, but our eyes don't respond as strongly to violet. Our retinas have fewer receptors sensitive to violet light, and the ozone layer also absorbs a lot of the violet radiation before it ever reaches us. What's left behind? That beautiful blue light. Our eyes are particularly tuned to perceive blue wavelengths, which is why the sky appears predominantly blue to us. It's not just about the physical scattering of light, but how our biology interprets those wavelengths. It's almost like our atmosphere and our eyes have evolved together, each fine-tuning its response to light. And it doesn't stop there. The interaction between sunlight and air molecules isn't just a one-off event. It's a continuous dynamic process happening every moment, every day. Every time you look up, the air molecules are scattering light, giving you that blue sky to enjoy. But it's all very delicate. If there were more or fewer molecules in the air, the whole scattering process could change, and the sky might look entirely different. Here's where the real surprise comes in. Some scientists have theorized that the color of the sky could actually be different if Earth had a different atmosphere. For example, if the atmosphere contained more carbon dioxide or other gases, the scattering effect could be altered, possibly changing the color of the sky. While this is just a theory, it shows how connected everything is. The tiniest shift in atmospheric composition could lead to a totally new visual experience. Pretty wild to think about, right? Dust, pollution, and why the sky isn't always blue. This is where things get a bit more complicated. While we like to think of the sky as consistently blue, there are days when things don't quite go according to plan. Have you ever noticed how, on some days, the sky looks kind of dull or gray instead of vibrant blue? Or perhaps on certain evenings, it feels like the colors of the sky are muted, as if something is getting in the way of the sunlight. It turns out that pollutants and particles in the atmosphere can have a massive impact on how we perceive the sky's color. Let's talk about dust first. Dust is a major player in this game, especially in areas near deserts or during dry seasons, when the air is full of tiny particles. When dust particles mix with the air, they scatter light in all directions, just like the oxygen and nitrogen molecules we talked about. But instead of just scattering blue light, dust particles tend to scatter all wavelengths of light more evenly, making the sky appear more washed out. On days when there's a lot of dust in the air, the sky can take on a grayish or even reddish hue, because the sunlight is being filtered through these scattered particles. Pollution does a similar job, but in its own unique way. Air pollution, particularly from car emissions and industrial activity, introduces even more particles into the atmosphere. These particles include soot, carbon, and various chemicals that not only scatter sunlight, but also absorb it. This absorption process can cause the sky to look even duller, especially in highly polluted areas. On smoggy days, the sun might look like a pale disk behind a thick gray blanket, and the sky can take on an almost sickly yellow or brown tint. It's not a pretty sight, but it's an important reminder of how much human activity can influence the natural world. There's an interesting tidbit here. While the pollutants and particles in the air may make the sky look gray or brown, they can also create spectacular sunrises and sunsets. When sunlight passes through a thicker layer of the atmosphere, as it does during dawn and dusk, the light is scattered more intensely. This results in beautiful red, orange, and purple skies. So in a way, pollution and dust don't just steal the beauty from the sky, they can add to it under the right conditions. The same particles that cause haze can, in the right light, create one of nature's most stunning visual spectacles. It's a reminder that even in the messiest of circumstances, there can still be beauty. And while we're on the subject of particles, let's not forget the role that water vapor plays. Clouds, which are made up of water droplets or ice crystals, are also part of this complex equation. Clouds scatter and reflect sunlight too. Depending on their thickness, clouds can make the sky look gray, or they can reflect sunlight in ways that create dramatic lighting effects. Clouds have their own kind of influence over the color of the sky, sometimes overpowering the blue with their thick white masses. Scientists still argue whether the particles in the atmosphere play a larger role in shaping sky color than previously thought. For instance, Researchers debate whether urbanization has made skies less vibrant over time, with the rise of industrial pollutants leading to longer-lasting haze. It's clear that what we see when we look up is influenced by a mix of natural and human-made factors, everything from the purity of the air to the shape and size of atmospheric particles. Red skies and sunsets, the flip side of blue. As the day progresses, something magical happens. When the sun starts dipping toward the horizon, we suddenly get a dramatic shift in the sky's color. What was once a bright blue sky now turns to shades of pink, orange, red, and sometimes even purple. It's a visual treat that most of us take for granted. But have you ever wondered why this happens? The main reason behind these spectacular sunsets is the same reason the sky is blue during the day: scattering. But here's the twist. During sunset, the light has to pass through a much thicker layer of the atmosphere. When the sun is high in the sky, sunlight only travels through a relatively short stretch of air before it reaches your eyes. But as the sun sets, the light must travel through a much larger portion of the atmosphere, scattering the light over a longer distance. As the sunlight passes through this thicker layer, the shorter wavelengths, blue and violet, get scattered even more, leaving the longer wavelengths, red, orange, and yellow, more prominent. Think of it as a game of hide and seek. The shorter wavelengths, like blue, are hiding away, scattered in all directions, while the longer wavelengths emerge victorious, traveling further and reaching your eyes. But it's not just the angle that causes the sky to turn red. Particles in the atmosphere, such as dust, pollution, and even water droplets, play a huge role. These particles further scatter the sunlight, often enhancing the reds and oranges. On particularly hazy or polluted days, the sky may look even more intense, with deep reds and oranges, creating that dramatic, fiery sunset. In fact, scientists have observed that after volcanic eruptions, the sky can appear even redder, as the ash particles suspended in the atmosphere can scatter sunlight in a way that enhances the reds and oranges at sunset. If you've ever been lucky enough to witness a vibrant, multicolored sunset, you've seen this process in action. It's a reminder that the sky's color is not fixed. It's in constant flux, influenced by the sun's position, the atmosphere's composition, and a few unpredictable variables. The same light that paints the sky blue during the day is also responsible for the warm hues of sunset, creating one of the most beautiful daily transitions on Earth. But not all sunsets are created equal. The clarity of the sky, the amount of moisture in the air, and the presence of particles can all affect how vivid or muted the sunset will be. Scientists still argue about how much of this is affected by human activity, particularly the increase in air pollution over time. While it's clear that natural processes play a major role, some studies suggest that urbanization and industrial emissions have made sunsets more vibrant and sometimes more frequent in certain regions. Well, it's a bit of a paradox. Pollution may be altering the color of the sky in ways we didn't expect, creating both negative and positive effects. What about the clouds? These fluffy, ever-changing formations that seem to play their own game with the sky. Clouds are often the unsung heroes when it comes to changing the color of the sky, and they certainly add complexity to our daily light show. While we're used to the idea that a clear sky equals a blue one, clouds throw a wrench into that system. They scatter and reflect light in ways that can make the sky appear anything but blue. Clouds are made of tiny water droplets or ice crystals, and when sunlight passes through or around them, the light gets scattered in all directions. However, clouds have a unique ability to filter out certain wavelengths of light, depending on their thickness and composition. When you look up at a cloud-filled sky, you're often seeing sunlight that's been diffused and softened, making the blue sky look less intense or completely hidden. On overcast days, this scattering is so strong that the sky can seem a flat, uniform gray, with no hint of blue at all. The more water droplets or ice crystals a cloud has, the thicker it is, and the more sunlight it can scatter. But here's a curious tidbit. When the sun is low on the horizon, as it is at sunrise or sunset, clouds can sometimes enhance the beauty of the sky, rather than obscure it. The warm hues from the sun, reds, oranges, and pinks, can be reflected and refracted by the cloud droplets, making the sky glow with vibrant colors. The clouds act like a canvas for the sun's last rays, turning the sky into a breathtaking masterpiece. These colorful clouds are especially prominent in the late afternoon when the sun's rays travel through more of the atmosphere, giving them time to scatter and reflect off the water droplets in the clouds. Interestingly, scientists still argue over exactly how much clouds contribute to the color of the sky. Some believe that the overall amount of sunlight scattered by clouds is the primary reason for their role in sky color, while others argue that it's more about the optical effects of the droplets themselves. Do clouds really change the hue of the sky more significantly than the scattering of light alone? It's a matter of ongoing discussion. While we may never come to a definitive answer, the sight of a cloud-streaked sky at sunset, or the shift in colors from blue to gray during a storm, remains an irreplaceable part of the natural world. Clouds in their varied forms are a reminder that the sky is never truly the same from day to day. They're part of a complex system that continually reshapes the atmosphere and its colors, showing us that even the most familiar sights are never static. From their ability to soften sunlight to their role in creating the most dramatic sunsets, clouds have a way of changing the narrative of the sky in ways we rarely stop to appreciate. Science, or art, why we perceive color the way we do. The color of the sky isn't just about what's happening in the atmosphere. It's also about how we as humans see the world around us. Perception of color is a fascinating mix of biology and physics. You might have noticed that the sky looks a certain shade of blue, but what's really happening when you look up? Your eyes are playing a crucial role in this visual experience. While the atmosphere is scattering light in all directions, it's your brain that ultimately interprets what you're seeing. So let's take a moment to dive into the science of how we perceive the color blue. Your eyes work in a surprisingly complex way. Light enters through the cornea, travels through the lens, and then hits the retina, where special cells called cones detect different wavelengths of light. These cones are responsible for your color vision. There are 3 types of cones: red sensitive, green sensitive, and blue sensitive. These cones work together to help your brain process the colors you see, but they're particularly sensitive to certain wavelengths. Blue light, with its shorter wavelength, is particularly well received by the blue-sensitive cones, which is why we perceive blue more intensely than other colors. Interestingly, humans have evolved to be more sensitive to blue light compared to violet, even though violet light is scattered more. This evolutionary quirk might be linked to the way our ancestors adapted to the natural world. Some scientists speculate that being more attuned to blue light helped early humans detect clear skies and good weather patterns, which were essential for survival. After all, clear skies typically meant a sunny day, which in turn meant better hunting and gathering conditions.
False.
It's one of those quirky aspects of human evolution that you don't really think about until you stop and analyze it. But here's where it gets a little more abstract. Our brains are not perfect interpreters of color. When we look at the sky, we might think it's a perfectly uniform blue. But in reality, the color you perceive could be slightly different from what someone else sees. The environment, the time of day, and even your mood can affect how you perceive the sky's color. Take the phenomenon known as color constancy. For example, this is a trick your brain plays to ensure that you always perceive the same color, even under different lighting conditions. So, while the sky may look blue during the day, your brain is compensating for the lighting and other factors, ensuring you see it as a consistent shade of blue. In a way, your perception is like a clever little cheat code, adjusting the sky's color to fit what your brain expects to see. But of course, not everyone perceives color the same way. Some people are colorblind and see the world in a different light. Scientists still argue whether color perception is a universal truth or a subjective experience. Some researchers believe that everyone sees color in essentially the same way, while others suggest that cultural and environmental factors can affect how we perceive the world around us. Could someone in a different culture see blue in a different shade based on their environmental cues or language? It's a question that doesn't have a straightforward answer, but it's one that makes you think about how subjective our experiences really are. The science of perception is still evolving, and each day, new discoveries are made about how our brains interpret the world. While we may never fully understand why we perceive blue the way we do, the very fact that we see a color so consistently, despite the changing conditions of the atmosphere, is a beautiful reminder of the wonders of our biology and the environment around us. Scientists still argue whether the sky is actually blue to us alone. Now, let's dive into a fascinating debate that has puzzled both scientists and philosophers for centuries. Does the sky appear blue to everyone, or is it simply a matter of human perception? While we may take it for granted that the sky is blue to all eyes, the question of whether all creatures see the sky the same way is still up for debate. This might sound like an odd question, but it turns out that how we perceive color is not just a matter of science. It's influenced by biology, evolution, and even philosophy. Humans, as we've discussed, perceive the sky as blue thanks to our eyes' sensitivity to shorter wavelengths. But what about other species? Dogs, for example, are known to have fewer color receptors in their eyes, meaning they don't see the full spectrum of colors like we do. Dogs primarily see shades of blue and yellow, so they likely perceive the sky in a different way. Even more fascinating, some animals like birds and insects have far more complex visual systems and can see ultraviolet light, a part of the spectrum that's completely invisible to us. Imagine a bird soaring through the sky, not just seeing blue but seeing ultraviolet patterns that we can't even begin to comprehend. So, are we all seeing the same sky? It's difficult to say. The color we see is the result of light interacting with our eyes, and that process can vary depending on the species. In fact, some scientists argue that the sky might not even be blue in a universal sense. Instead, it's blue to us, thanks to the combination of the Rayleigh scattering effect and our unique visual system. This means that the sky's blueness is in part a construct of human perception. What we see is deeply tied to our biology. Our retinas, the cones that detect color, and how we process that information in our brain. But here's where it gets even more mind-bending. Some researchers believe that we might not even be seeing the full range of blue in the sky, because our brains are filtering out certain wavelengths or adjusting them to fit our cognitive model of color. In other words, the blue we see might not be the true blue of the sky. It's just our brain's best guess at what it should look like. This theory opens up a whole new world of questions. Could there be shades of blue that we're simply unable to detect? And if our experience of color is subjective, how can we ever truly know if what we see is the same as what someone else sees? The concept of subjective perception is deeply fascinating. While we agree that the sky is blue, this could be a collective human agreement, influenced by language and shared experience. Scientists still argue about how much of our perception is shaped by the brain versus the environment. Could it be that the sky's blueness is an illusion, a shared experience crafted by our biology? Or is there something more to it that we're missing? Ultimately, what we perceive as blue might only be blue to us. It's a reminder that our understanding of the world is inherently limited by our senses. The same sky that stretches above us is perceived differently across species, cultures, and even individual experiences. It's a beautiful paradox. The sky we all share might look completely different to someone or something else. Atmospheric effects in different parts of the world. So far, we've explored how the scattering of light creates the blue sky we know and love. But did you know that the color of the sky can vary dramatically depending on where you are on Earth? The atmosphere isn't a uniform layer all around the globe. It's shaped by a variety of environmental factors that change from place to place. In fact, the sky you see in one part of the world might look drastically different from the sky in another. Let's take a closer look at how location, weather, and even altitude can change the color of the sky. For starters, the angle at which sunlight enters the atmosphere can have a huge impact. All in places closer to the equator, where the sun is higher in the sky, the light has to travel through less atmosphere. This means that the shorter wavelengths, blue light, are scattered more directly toward your eyes, making the sky look brighter and more vivid. In tropical areas, you might notice that the sky seems a particularly intense blue, as the sunlight is almost directly overhead, scattering that blue light in a very focused way. But the story doesn't end there. Altitude plays a role too. In higher altitudes, such as in mountainous regions, the air is thinner and there are fewer particles to scatter light. This means the blue in the sky can appear deeper and more intense, as the sunlight has less interference. When you're up in the mountains, you might notice that the sky seems to have a sharper, more brilliant blue, almost as if the air itself is filtering the light to make it appear more vibrant. Now, consider regions with a lot of pollution, like large industrial cities or heavily populated areas. All pollution can create a thicker atmosphere, and the particulate matter in the air scatters light differently. This often results in hazier skies, with less intense blue, and sometimes even a yellowish or brownish tint. Smog, dust, and other pollutants can scatter light in all directions, making the sky appear dull or even a dirty gray. On days when there's a lot of smog in the air, the sky might look like a pale, washed-out version of blue, and the sun may seem to fade into a hazy orb. Then there are areas near large bodies of water, like coastal regions, where the sky might appear softer. The ocean reflects light in unique ways, and the moisture in the air can add a slightly different texture to the light, making the sky appear lighter or even more muted. Coastal skies might also experience more cloud cover, which changes the appearance of the blue sky. In places like this, you might notice the blue sky is often dotted with clouds, creating a more dramatic effect when sunlight breaks through. And of course, time of year plays a role too. In winter, the sun is lower in the sky, and the light has to travel through more of the atmosphere, leading to more scattering of the shorter wavelengths. This is why the winter sky can sometimes appear lighter and less vibrant than during the summer when the sun is higher. The amount of dust, pollution, and moisture in the air fluctuates with the seasons, further influencing the sky's color. Scientists still argue about the degree to which regional factors affect sky color. While it's clear that altitude, pollution, and location all play a significant role, some researchers wonder how much of the perceived difference in sky color is due to the varying compositions of the atmosphere in different parts of the world. Could it be that environmental changes are making the sky appear even bluer or more muted than it used to? The debate continues, but one thing's for sure: the sky isn't a one-size-fits-all phenomenon. It's shaped by everything from geography to climate to human activity. Could the sky change color in the future? It's a question that seems almost too big to ask, but it's one that increasingly needs to be addressed. As we look at the effects of climate change and environmental shifts, scientists are beginning to wonder whether human activity could actually alter the color of the sky itself. Imagine this. What if the sky didn't look as blue as we know it today? Could that sunny, endless expanse above our heads change forever? It's It sounds far-fetched, but it's not entirely out of the realm of possibility. One of the most significant factors that could affect the color of the sky is the increase in greenhouse gases and air pollution. As the global climate continues to warm, the atmosphere is changing, and the composition of gases within it is shifting. We're already seeing the impact of rising carbon dioxide levels and the growing number of pollutants in the air. These changes could affect how light scatters through the atmosphere, potentially altering the color of the sky in ways we can't yet fully predict. For example, the higher concentration of pollutants, like particulate matter from industrial activities, could cause the sky to look even more muted. This is something we're already seeing in heavily polluted areas, where the sky can appear gray, brown, or even orange due to the increased scattering of light. If air pollution continues to rise at the current rate, it could mean that the vibrant blue sky of today becomes a rarer sight, replaced by duller, more polluted skies. This could be especially true in urban centers or industrialized regions, where smog and haze are becoming more common. But the effects might go beyond just pollution. The increasing concentration of carbon dioxide in the atmosphere could lead to shifts in weather patterns, which might change the way light interacts with the atmosphere altogether. Warmer temperatures could lead to more intense thunderstorms or longer dry periods, which would impact the presence of clouds, moisture, and pollutants in the air. These factors would have a direct impact on how much light is scattered, and consequently, how we perceive the sky. If the frequency or density of clouds changes, it could mean more gray skies, or in extreme cases, even more vivid and unpredictable sunsets. Another possibility is the increase in wildfires due to climate change. Wildfires, particularly in places like the American West or Australia, produce huge amounts of smoke that can travel thousands of miles, affecting the appearance of the sky. The smoke particles in the atmosphere scatter light in a way that makes the sky look hazy or even completely red. Some scientists have already noted that wildfires are making the skies in certain regions look more orange, particularly during sunrise and sunset. In the future, it's possible that more frequent wildfires could lead to more pervasive changes in sky color, especially during certain times of the year. On a larger scale, changes in the ozone layer could also affect how we see the sky. The ozone layer is responsible for filtering out harmful ultraviolet rays from the sun. As it depletes, it could alter the way sunlight interacts with the atmosphere, potentially affecting the colors we see in the sky. While the connection between ozone depletion and sky color isn't fully understood, there's a possibility that shifts in ozone levels could lead to changes in the intensity and quality of the light that reaches us. One thing's for sure, the future of our skies isn't entirely certain. As we continue to change the world around us, the atmosphere we depend on may undergo alterations that could shift the colors we take for granted. What we consider a blue sky might not always be so clear or vibrant. In fact, some researchers argue that we could be heading toward a future where the sky is not as bright and perhaps not as blue as it once was. It's a sobering thought, but also a reminder of how deeply interconnected we are with the environment around us. If we don't take care of the atmosphere, it could eventually change the very color of our world. What other things affect the sky's appearance? You might think of the sky as a simple, consistent feature of our world, but it's actually a dynamic, ever-changing canvas influenced by many factors. We've already touched on how pollutants, altitude, and the time of day can change the way the sky looks, but there are a few rare phenomena that can create some truly extraordinary changes in sky color. From volcanic eruptions to cosmic events, the sky has a way of surprising us with a whole new set of colors and moods that seem to defy the usual rules. Take volcanic eruptions, for example. When a volcano erupts, It doesn't just send lava flowing down the sides of the mountain. The eruption releases enormous quantities of ash and gases into the atmosphere, including sulfur dioxide. These particles can travel great distances and create dramatic effects on the sky. One of the most famous examples of this occurred in 1991, after the eruption of Mount Pinatubo in the Philippines. The eruption released so much ash into the atmosphere that it caused a global cooling effect and dramatically altered the appearance of the sky for months. The particles in the air scattered light in a way that created deeper, richer sunsets and sunrises, as well as a more muted blue sky during the day. In fact, some scientists believe that volcanic eruptions have the power to alter sky colors on a global scale, potentially affecting everything from the intensity of sunsets to how blue the sky appears during the day. Similarly, large forest fires can have a similar effect on the atmosphere. Wildfires release huge amounts of particulate matter into the air. Much like volcanoes do, these particles scatter and absorb sunlight, often causing the sky to appear a strange mix of smoky gray, orange, or even red. During major fire seasons, you might notice that the air feels thick and hazy, and the sky has a strange, unsettling glow. It's the same effect that gives us those dramatic red sunsets after a wildfire, except that it can often turn the sky itself into a smoky haze for days, weeks, or even longer. The impact of forest fires on the sky can be so dramatic that entire regions can experience a dull, fiery orange glow during daylight hours, making it feel like you're walking around in a surreal, otherworldly environment. Astronomical events also have the potential to change the sky's appearance in more unexpected ways. While we're accustomed to the phases of the moon, the positions of the stars, and the occasional meteor shower, a total solar eclipse is one of the most jaw-dropping events that can affect how we perceive the sky. When the moon passes directly in front of the sun, the world is plunged into temporary darkness. During this brief period, the sky takes on an eerie twilight color, as if it's evening, even though the sun is supposed to be in the sky. The surrounding atmosphere behaves differently as well, as the temperature drops and the sunlight is blocked. The sky can appear dark and dramatic, with the light scattering in a way that creates vibrant hues of purple, pink, and orange in places where the sun is obscured. It's a moment where the rules of sky color are completely thrown out the window. Even the arrival of dust storms or unusual weather patterns can create rare and beautiful sky colors. Dust storms, especially those in arid regions like the Sahara Desert, can carry dust particles high into the atmosphere, coloring the sky a deep reddish-orange as the particles scatter the sunlight. These storms can affect areas far beyond their point of origin, altering the color of the sky in places that would normally enjoy bright blue skies. The phenomenon of blood moons, which occurs when the moon passes through Earth's shadow during a lunar eclipse, is another unique event where the sky and even the moon itself appears red, thanks to the way sunlight bends around the Earth's atmosphere. It's fascinating to think about how the sky can appear so different depending on where you are, when you look, and what natural phenomena are taking place. The blue sky that we often take for granted is far from a constant, and there's a whole world of variables and unusual events that can alter its appearance. From volcanic ash to cosmic events, the sky is an ever-changing canvas, sometimes blue, sometimes fiery red, and sometimes filled with strange, smoky hues that remind us just how powerful and unpredictable nature can be. Why it's good to remember that sometimes the sky's beauty is just the backdrop. After everything we've learned about how the sky's color changes and what influences it, it's easy to get lost in the science of it all. But sometimes the real beauty of the sky lies in the simplicity of it, uncomplicated by scientific details, free of the debate over whether it's blue or violet or redder than usual due to the latest wildfire. The sky has an uncanny ability to soothe and inspire, and perhaps the most powerful thing it offers is its constant ability to be both familiar and new at the same time. In a way, the sky is a reflection of life itself, always shifting, sometimes calm and serene, other times wild and unpredictable. We go through our daily routines, often looking up without giving much thought to what's above us. But when we take a moment to really look, the sky reminds us of something fundamental. Everything is constantly changing. Just like the sky, we are subject to shifts, storms, and moments of quiet. And much like the beauty of the sky, our lives, too, hold moments of peace, intensity, and surprise. The sky isn't just a background for our lives. It's a mirror of life's own ebb and flow. Perhaps that's why it feels so special to witness a sky full of vibrant colors. Whether it's the blue of a sunny day or the fiery reds and purples of a sunset, those moments connect us to something larger than ourselves. They remind us of the beauty in the natural world, of things much bigger than the daily grind we get caught up in. The way the sky changes can give us a sense of calm, of wonder, and sometimes even of awe. The next time you find yourself gazing at the sky, maybe take a second to appreciate how, despite everything else going on in the world, this ever-changing celestial display is always there. It's a backdrop, yes, but also a testament to the beauty that exists in the world, sometimes hidden in the most unlikely places. So as you lie back tonight, staring up at the darkening sky, or perhaps the deep blue or fading orange hues of dusk, remember that this is more than just a color we see. It's a reminder of the mysteries, the forces of nature, and the balance of life all around us. The sky will always change, always surprise us, but in that change, there's a quiet reassurance that we're all part of something much bigger. Now, as the sky darkens and the stars begin to twinkle, take a deep breath, relax, and allow your mind to wander. Because just like the sky, you too can embrace the ebb and flow of your own journey.